Okay, this is the homework part. This is the homework part of 9.4. All right, let's take a look. Remember, most of this stuff is going to deal with the p-series and geometric series. So in this first one, this is the series we're trying to figure out if it converges or diverges. And once again, this is a very complex problem, but it's really similar to this problem. There's just not the +6 after it. This is a p-series problem. This is not. But we can determine whether the p-series converges or not. First thing we have to determine if our simpler one is larger than the more complex problem. In other words, is this true? And it is true because you can plug any number greater than 1 into this. If you plug any number greater than 1 into this, here you get 2. Let's say plug in 2. 2 times 2 is 4, times 2 is 8, 16, 32, 64. So here you get 1 over 3 times 64. 3 times 64 is 192. And then if you add 6 to it, you get 198. And this is 192. And sure enough, if the denominator, if they both have 1 on top and the denominator is larger, then the entire number is smaller, right? If your denominator is larger than the other denominator, and they have the same thing on top in the numerator, then the number is smaller. So yes, this holds true. The complex problem is smaller than the easier p-series problem. And that's what we want. We want the p-series, the problem that we can determine whether converges or diverges, to be larger, or you can't continue. So we know it's larger, and we just have to determine if this converges or diverges. P-series test, when there's 2 things, when p is greater than 1, then the series converges. If p is between 0 and 1, it diverges. Well, here's p. P equals 6. So the series does converge. This converges by the direct comparison test. This also converges. So that's what we're doing here, comparing an easier version of these complex problems. Finding out if the easier version is larger, and if it is, then determining if the easier version converges or diverges, and the same thing happens to the more complex problem. Question 2. If we try to compare this is n 6 over 7 minus 1. And we want to know if this is smaller than the easier version, and the easier version is just 1 over 6 over 7. 2 times 2 is 4, times 2 is 8, times 2 is 16, 32, 64, 128. So I can put any number in here, and I'm going to put n equals 128 in here because it's an easy number to work with if you look at this. If I put 128 to the 6 over 7, well, the 7th root of 128 is 2. 2 to the 6th power is 64. So this is 64. 64 minus 1 is 63. And this is just, if I put 128 into here, I get 64. So when you look at this denominator is smaller than the other one. So this number is larger. So this time, the more complex number is larger. The first problem, the easy problem is we want to continue, we want this be larger. We want this number, the easy problem, to be larger, but it's not. It's 1 over 64 is smaller than 1 over 63. So automatically, we don't go on. We just say the problem diverges. The easier version has to be the larger number when you're comparing the two and plugging numbers into it. So question 2 diverges. All right. Going to question 3. Question 3, we have 7n over 8n plus 5. And is this smaller than 7 over n, 8n, without the plus 5? And if you plug in some numbers into here, anything over 1 or even 1, sometimes 1 doesn't work, but if you plug anything over, I just plug any number like 2, what happens is you add 5 to this number. So the denominator, I'm not even looking at the top, I'm not even going to do the math. I just know the denominator is larger than this denominator. This denominator is smaller. When you plug in n equals 2. When you plug in n equals 2, this is going to have a larger denominator. If you have a larger denominator, then the entire number is smaller. If the denominator is larger and both have the same numerator, then the entire number is smaller. So we're good to go. So we can use the direct comparison test. We can use then the direct comparison test here. So I'm going to erase this, and we're just going to look at this. And another way of writing this, by the way, is 7 over 8 to the n, right? When you have an n power, you can bring it out to make it look like this. And this is the geometric system. And r equals, that's r equals 7 over 8. And for geometric, when r is greater than or equal to 1, the whole, by the way, it's always the absolute value, but when r is greater than or equal to 1, the whole thing diverges. If r is less than, not less than or equal to, just less than 1, it converges. Since 7 over 8 is less than 1, the whole system converges. This converges, which means the more complex converges, because this is larger. The entire number is larger than the other one. And so then the more complex does converge. So this system does converge. And when you put this in here, you would just say, yes, this side is smaller than the other fraction that we're going to deal with. You know, the one we put in there, 7 raised to the n power over 8 raised to the n power. So the whole thing does converge. question 4. And question 4 is a little bit tougher. This is one that you're going to have to remember. You really do have to remember how this one's going to play out. And the way I look at it is this. If I plug in 0 into here, 1 over 0 factorial is 1. If I plug in n equals 1, 1 factorial is 1. If I plug in n equals 2, 2 factorial is 2. If I plug in 3, 3 factorial, 3 times 2 times 1 is 6. If I plug in, what I plug in? 0, 1, 2, 3. If I plug in 4, I get 4 factorial, which is 24. And then I can actually plug in 5. I get 120. 5 factorial is 120. This is when n equals 5, n equals 4, n equals 0. So if you look at that, it starts with 0. So it kind of looks like, well, it is a P series. I mean, kind of like a P series. We'll show you. This is not a P series, but we want to get something that's really similar to this, that's working, and it has to be larger. 1 over n factorial has to be smaller than what we're dealing with. And what they're saying is, in the book shows this, that try using 1 over n squared. Try using 1 over n squared. And let's try that. And so I'm going to use 1 over n. This is n factorial. Let's, below this, I'm going to put n squared. And if I put 0 in there, I end up with 1. If I put 1 in there, put 1 into the, well, 0 squared is 0, sorry. If I put 1 in there in n, I get 1 squared, which is 1. If I put 2 in there, oh wait, it's supposed to be 1 over n squared, sorry. If I put 0 in there, I get undefined. If I put 1 in there, I get 1. If I put 2 in there, I get 1/4. If I put 3 in there, I get 1/9. If I put 4 in there, 4 squared is 1 over 16. If I put 5 in there, I get 1 over 25. So this is really important. Here, the numbers are the same. This, and I'm going to circle the larger ones in red. This one is larger than the 1/4. 1/6 is larger than 1/9. However, this is larger than 1 over 24. This one is larger. This one is 1 over 25 is larger than 1/20th, and so on. So all the larger numbers will be here. So we can do this comparison, and this is for n equals 1, 2, 3, 4. We can do this comparison just as long as we're dealing with these numbers and not these. That's why we say this holds true. This right here, it holds true. This, since these numbers, the n squares are larger, but they're only larger when n is greater than 3, when we start with n4, n5, n6. So this does hold true if n is larger than 3. And that's why they say this. We can compare these two if n is greater than 3. And I don't know why they did this backwards, but I mean, we should do it the way we've been doing it and the way the theorem says to do it. The 1 over factorial should go on the left. It's smaller. And this is, I mean, they do it here. This is smaller. It's the less than symbol pointing at it. It is smaller, but this is the way we've been doing it. So I don't know why they changed it all of a sudden. So this holds true anytime n is greater than 3. So the only thing we need to do for this problem is determine if 1 over n squared converges or diverges. This is a P series, and this is the P. P equals 2. And if you remember for P series, between when P is between 0 and 1, it diverges. And if P is greater than 1, it converges. P equals 2, it's greater than 1, so the whole series converges. This converges, which means it's more complicated. The factorial one also converges. So that factorial is a little tough. Just remember, you're going to compare it with 1 over n squared. And there's one more problem I wanted to do, problem 8 in the homework, the last one here. I just wanted to show the reasoning and thinking. I mean, if you didn't have this, it's a hard thing to look at. This is a hard series to look at to figure this out. But they show you this is the series 1 over 500 plus n squared. Do you see if n is 1, 1 squared is 1. N is 2, 2 squared is 4. 500 plus 4 is 504. If n is 3, 3 squared is 9, so you get 509. This is the series we're looking at. We want to verify that this is smaller than a more simpler series, this right here. And it is, you plug any number in here, the denominator is larger, D is larger, so the whole problem is smaller. The whole number is smaller than this one. So that checks out. So we just need to do, once again, whether this, whether 1 over n squared converges or diverges, P equals 2. And we know when P is greater than 1, the whole system converges. So this series does converge. All right. I hope that helped in the homework. You guys have a good day, and email me if you have any questions.